This is the third module and addresses learning objective number 3. Apply these genetic and statistical principles to the interpretation of DNA test results. The module learning objectives are: describe and apply the random match probability, describe and apply the probability of exclusion, and describe and apply the likelihood ratio. I will take you through the material using slides and also some video clips from a workshop presented for NFSTC by Dr. Greg LaBerge, Director of the Denver Police Department Crime Laboratory. There are generally 3 statistical approaches used in forensic DNA interpretation. 1. Full Bayesian, 2. Frequentist or coincidence, and 3. Logical or likelihood ratio. Each approach requires the use of allele frequencies, which are calculated from various databases. This module will focus on the frequentist and logical approaches, the most widely used statistical approaches in the United States. We're going to begin by discussing the frequentist approach. The frequentist approach uses probabilities or genotype frequencies to address statistical questions. Coincidence probability, or the random match probability, and the probability of exclusion are each frequentist approaches that are applied by the forensic science community. The coincidence approach assesses whether or not the match between the DNA profile obtained from the evidence and the DNA profile obtained from the suspect occurs by chance or coincidence. Allele frequencies are calculated using data that assumes Hardy-Weinberg equilibrium and no linkage disequilibrium. Homozygote frequencies are determined by p squared and heterozygote frequencies by 2pq, the Hardy-Weinberg formula. The autosomal STR loci used by the forensic science community are not linked, and therefore the genotypes from each locus can be multiplied using the product rule to obtain the frequency of the combined individual genotypes. As discussed in Module 1, a theta correction can be applied to random match probability formulas. This slide shows the formulas incorporating theta. Here is a video of Dr. Greg LaBerge illustrating the theta correction as recommended in NRC 2.
Okay, there's the formula you use. NRC 2, which is that yellow book, recommendation 4.1, they ask you to do a correction on the homozygotes, right? Instead of just using p squared, which is Hardy-Weinberg's, they're telling you to say p squared and then add that thing to the right of it, which is just p, which is the allele frequency for that locus that you're looking at, times 1 minus the allele frequency times 0.01, right? So try it. Say your allele frequency is 0.3. What's 0.3 squared is what? 0.09 plus 0.3 times 0.7 is what? 0.21. What's 0.21 times 0.01? Just shift the decimal place. And add that to 0.09. What do you get? 0.092. Right? Is that much different than 0.09? So with common alleles, it doesn't change them much. Right? So that if you have common alleles and you add this correction factor for population stratification or population inbreeding, which could lead to a departure in Hardy-Weinberg equilibrium, if it existed, for common alleles, it's not going to change it much at all. Right? Why don't we correct heterozygotes? When you have inbreeding, you're increasing homozygosity. Okay? So what they're trying to do is they're saying, well, if there is inbreeding, you want to correct so that you're making the homozygotes more common, right? To account for possible inbreeding. So what they're saying is your population numbers that you're calculating aren't accounting for inbreeding. So they're too rare. So you got to make your homozygotes more common to be more reflective if there was inbreeding. You see that? You're increasing the frequency of the homozygotes as if there was 1% inbreeding. Your heterozygotes, if there was, are going to be an overstatement of what they should be.
The frequency obtained from the random match probability calculation for the purposes of this training, can be expressed as the coincidence that an unrelated person would by chance have the same DNA profile as that obtained from the evidence. One way to phrase this in a forensic case could be to state that either the suspect contributed the evidence or an unlikely coincidence has occurred. The probability of exclusion is generally used for mixture situations. This formula provides an estimate of the proportion of the population that has a genotype composed of at least one allele not observed in the mixed profile. Each locus is still treated independently and assumed to be in Hardy-Weinberg equilibrium. Therefore, the probability of exclusion calculated at each locus can be multiplied together for combined probability of exclusion. One way to calculate the probability of exclusion for a locus is to calculate 1 minus p squared for each allele and add each together. To incorporate a theta correction, the formula could be modified to 1 minus p squared plus theta times p times 1 minus p. Here is a video of Dr. Greg LeBerge discussing the probability of exclusion.
Remember, the random match probability is just that, and the exclusion probability, and you'll hear them call it a probability of exclusion, is 1 minus the random match probability, which is usually 99.999 something, right? What is the exclusion probability? What is it in words? Well, it's probability that you would exclude a random person from the population by chance, right? Now, we ran into this up at the RCMP in Canada, and they were using the probability of exclusion routinely, and I jumped on them at a scientific meeting and said, actually it was my colleague, and we both were back there criticizing him. I got notorious in Canada for that. You don't criticize the RCMP. But I did because I don't work for them, and I'm in the States. It was a little bit of fun. I said, you can't exclude anybody until you genotype them. Right? They're like all standing there kind of looking at us. Like, yeah, you're right. So theoretically, you can theoretically exclude someone, or you can theoretically exclude the population of Ontario, but could be still that same thing, could be still the next person you genotype, could be the person. And you can't really exclude anybody until you genotype them, right? So you can use that. You can use the exclusion probability if you want, but just watch that.
What is meant by the frequency of the matching profile is 1 in 57 billion. It is an estimated probability obtained by multiplying together the allele frequencies and refers to an infinite, randomly mating population. It has nothing to do with the size of the world's population. We will now look at the likelihood ratio formula. In order to understand the likelihood ratio, we need to go through some background information. We will start with Bayes' theorem. Thomas Bayes was an 18th century clergyman who developed a formula for calculating conditional probabilities. The formula is that the posterior odds are equal to the likelihood ratio times the prior odds. When applied to forensic DNA analysis, two competing hypotheses are assessed. These are often referred to as the prosecutor's hypothesis and the defense's hypothesis. This slide shows the formulas with the sections of the formulas labeled posterior odds, likelihood ratio, and prior odds. Prior odds are considered the odds on the hypothesis prior to the DNA evidence. When presenting DNA evidence as scientists, we generally avoid any discussion on prior odds. These odds are generally not given a numeric value in the United States. It is the judge and jury's job to assess the weight to be given to prior odds. Given that, the formula can be modified to the probability of the evidence given the prosecutor's hypothesis divided by the probability of the evidence given the defense's hypothesis. H subscript P represents the prosecutor's hypothesis, and H subscript D represents the defense's hypothesis. The likelihood ratio is the ratio of two probabilities of the same event under different hypotheses. So, for events A and B, the probability of A, given that B is true, hypothesis number 1, divided by the probability of event A, given that B is false, hypothesis number 2, gives a likelihood ratio. The likelihood ratio is a ratio of probabilities, and it can take a value between 0 and infinity. The higher the ratio, the more likely it is that the first hypothesis is true. Here is Dr. LeBerge, this time discussing the likelihood ratio.
The likelihood ratio, you're going to hear them talk about the likelihood ratio. And this is kind of a messy way of showing what the likelihood ratios are. You don't need to write this down. This is too complex, and I'm not going to ask you to regurgitate it. But in general, the general statement that I've heard as it used when it applies to a random match probability is the numerator, and I'll go to my little board here. The likelihood ratio is equal to the probability of the evidence given that it came from the suspect over the probability of the evidence given that it didn't come from the suspect. It's a general form, okay, for a random match probability setting. So what do you think the numerator is? Probability of the evidence given that it came from the suspect.
1.
Yep. Why?
If you're given that it came from the suspect, it had to have come from the
100%.
suspect.
Right. What's the probability of the evidence given that it didn't come from the suspect? Or just a random person in the population? Random match probability, which is a fraction in itself, equals what? Well, let's say this is 1 in 100. What's 1 over 1 over 100? 100. What does that mean? The way the words go with this, it's the probability. It's 100 times more likely that the DNA from the evidence and the suspect are from a common source than not. That's a hard one sometimes for the jury to really kind of look at you like, huh? The likelihood ratio is actually a good way to do things in a mixture scenario more than it is in a random match situation. Because the court wants to know what's the probability of seeing this profile by chance. You know, in a single source, do you guys in single source do LRs?
Well, we can do both. We can do either random match
Yeah,
probability or
and
likelihood
they're
ratio.
interchangeable because the denominator is the defining thing in these things. They're related. It's 100 or 1 over 100. But in a mixture scenario, it allows you more flexibility in terms of the numerator, okay? And I used to have to argue with a guy I work with because he couldn't understand why the numerator couldn't be 1. Well, there's different conditional probabilities in a mixture. You can say the probability in the numerator is that it's the victim is in the mixture and an unknown, like a 1 known, 1 unknown mixture, versus 2 unknowns in the denominator. It's 2 competing hypotheses, right? Well, that's all it is. It's a likelihood in the numerator, a likelihood in the denominator, right? In mixtures, it allows you more flexibility in how you calculate things. And it's not a bad thing to do. The problem is it's really tough in terms of software available out there to do it.
When applied to forensic DNA analysis, the following equation can be used to determine the probability of the evidence given that a presumed individual is the contributor rather than a random individual in the population. The likelihood ratio equals the probability of the evidence given the prosecutor's hypothesis is correct, divided by the probability of the evidence given that the defense's hypothesis is correct. Or, it can also be stated as the probability of the evidence given a presumed individual is the contributor versus the probability of the evidence given the presumed individual is not the contributor of the evidence. In the case of a single source sample, the hypothesis for the numerator is that the suspect is the source of the DNA, and therefore the numerator is reduced to 1. This reduces the formula, 1 divided by the probability of the evidence, given that the defense's hypothesis is correct, or 1 over p, where p is the genotype frequency. The use of the likelihood ratio for single source samples is simply another way of stating the probability of the genotype, and while stated differently, results in the same value as the random match probability approach. Although likelihood ratios can be used for determining the significance of single source crime stains, they are more commonly used in mixture interpretation. One example for a 2-person mixture is the prosecutor's hypothesis is that the contributors were the victim and the suspect. The defense's hypothesis is that the contributors were the victim and an unknown individual. This slide shows the allele calls for the evidentiary mixture. This slide shows the known genotypes for the victim and the suspect. If both the prosecutor and defense hypotheses include the victim, then we become interested in the alleles that could have been contributed by someone else. At D3, S1358, the evidence profile is 15. The victim also is a 15. Therefore, assuming all alleles from both contributors are present, then the second contributor is a 15. For VWA, the evidence profile is a 1617. The victim is also a 1617. Therefore, assuming all alleles from both contributors are present, the second contributor can be a 1616, a 1617, or a 1717 genotype. For D8 S1179, the evidence profile is 1216. The victim is a 12. Therefore, assuming all alleles from both contributors are present, the second contributor can be a 1216 or a 1616 genotype. For D21 S11, the evidence profile is a 30, 31.2, 32.2. The victim is a 30, 32.2.
32.1.
Therefore, assuming all alleles from both contributors are present, the second contributor can be a 31.2, 31.2, a 30, 31.2, or a 31.2, 32.2 genotype. The likelihood ratio is calculated by evaluating each locus, determining the probability of each possible genotype for the second contributor, and adding each genotype probability for each locus. Then, the values for each locus are multiplied together to obtain the total likelihood ratio. One way to state the likelihood ratio, assuming it is greater than 1, is to say, based on the statistics, it is more likely that it is the victim and the suspect who contributed the profiles found on the evidence than the victim and a person selected randomly from the population. A theta correction can also be applied to the likelihood ratio. This slide shows the formulas for both homozygotes and heterozygotes with a theta correction. The likelihood ratio does rely upon two competing hypotheses. Forensic DNA analysts must determine the parameters of each hypothesis prior to applying this formula. For example, the total number of contributors, the number of unknown contributors, and the number and genotype of known contributors. In addition, the use of any formula for mixture interpretation should only be applied to cases in which the analyst can reasonably assume that all contributors to the mixed profile are unrelated to each other and that allelic dropout has no practical impact. The objective of this module has been to provide you with the basic understanding of the tools that we use to interpret and report DNA results. In practice, this is not a problem, as the CODIS software that crime laboratories use includes a statistics module, PopStats. The next slides illustrate the operation of PopStats and are taken from material made available courtesy of the FBI. First, there is a data entry screen, whereby the alleles for the loci can be entered for each sample. If we zoom in on the top left-hand corner of the data entry table, we see that it lists the CODIS core loci with fields for entry of the alleles detected. The next slide shows the calculated frequencies in each of the racial ethnic populations included in the CODIS database, together with data corrected for relatedness. If we zoom in on the top left-hand corner of the screen, we see the genotype frequencies for each locus and the CODIS database that they are calculated from. Zooming into the bottom left shows the number of alleles present in the databases. The bottom right corner of the screen shows genotype frequencies corrected for certain degrees of relatedness, calculated for each of the database populations. The last screenshot shows the results of the probability of exclusion calculations on the data, again with separate results for each population. The top left of the screen is the locus and allele data entered, and the bottom right of the screen shows the exclusion or inclusion statistics. This shot is of the exclusion values. Each laboratory will have its own protocol for interpretation of results. Although it is easy to follow these, it is important that you understand what you are doing, especially in mixture interpretation, and that is the aim of this module and indeed the course on population genetics. To test your understanding of the interpretation of test results module, please work through the review questions. Number 1, define the random match probability and identify which of the laws of probability is used to calculate the random match probability. Without using PopStats and taking Caucasian allele frequencies from the Starbase website to calculate the random match probability for the profile listed on the screen. Number 2, when would probability of exclusion be used and how is it calculated? Calculate the probability of exclusion for the above profile in the African American population. Do not use PopStats. Number 3, what is the formula for likelihood ratio in a single source situation? Calculate the likelihood ratio for the above profile in the Hispanic population. Do not use PopStats. Number 4, refer to the slide and text for likelihood ratio calculation in a mixture. Calculate the likelihood ratio for the alleles on the screen. Number 5, what would you do if it was not possible to be sure that all contributors to a mixture were unrelated to each other? Number 6, research the prosecutor's fallacy and explain how this is different from the prosecutor's hypothesis.